Take a moment now to settle yourself. Lie down, close your eyes, and let the world around you dissolve into quiet stillness. Allow your breathing to slow, each exhale a gentle wave carrying you into a space of calm observation, where the past and the present meet silently. Have you ever wondered what life looked like in places that no longer exist? Across the sweep of time, entire ecosystems have vanished, leaving behind traces only in sediment, fossils, and the quiet imagination of scientists who reconstruct their former richness. The Earth was once stitched together with forests, wetlands, coral reefs, grasslands, and islands so distinct in their life forms that they seem like worlds apart from anything we can witness today. To explore them is to wander through spaces both intimate and vast, where the flora and fauna were tuned to climates and conditions that have long since disappeared. In the earliest large forests, during the Carboniferous period, roughly 359 to 299 million years ago, the planet was cloaked in dense equatorial rainforests. Towering lycophytes, tree ferns, and horsetails stretched hundreds of feet, their fronds forming a perpetual canopy that filtered sunlight into a green-shadowed world below. Massive insects, such as dragonfly-like Meganeura, with wingspans exceeding 2 feet, patrolled the still, humid air, while early amphibians wove silently through the undergrowth, moving between shallow pools and moss-covered logs. These forests were crucibles of life and carbon. Their dense vegetation contributed to significant coal deposits over millions of years, a record of ecosystems that no longer breathe on the Earth's surface. Their disappearance was gradual yet inexorable, as climatic cooling and glaciation reshaped the continents, altering rainfall patterns and drying the once pervasive humidity. Transitioning from these prehistoric woodlands, vast wetlands and peatlands emerged across continents, places where water lingered long enough to saturate soil and nurture unique assemblages of plants and animals. European fens, North American marshes, and Asian swamps harbored plants that thrived in waterlogged soils, sedges, reeds, and aquatic mosses forming complex mats that captured nutrients and supported insect populations unique to these liminal environments. Birds and amphibians, some now extinct, relied on these wetlands as breeding grounds and migration stopovers. Humans, arriving much later, often reshaped these landscapes, draining swamps for agriculture or urban expansion, erasing the complex waterborne networks and leaving behind monocultures that bear little resemblance to the ecosystems they replaced. Beneath the waves, ancient coral reefs painted shallow oceans with vibrant life. Fossilized reefs, now lithified in limestone, reveal colonies of corals and sponges that supported fish species, mollusks, and echinoderms, unlike those alive today. In the Permian period, reef systems thrived in tropical seas, yet shifts in ocean chemistry, global warming events, and massive extinctions transformed these reefs into silent stone remnants. Coral bleaching events and acidification in modern oceans echo similar processes that led to the disappearance of entire reef ecosystems, though the scale and rate today are unprecedented. Light would once have refracted through the shallow, clear waters, illuminating patterned coral surfaces and the iridescence of fish scales. A visual richness now vanished from these sites forever. Across continents, grasslands and savannas carried life adapted to open, sun-drenched landscapes. North American prairies, Eurasian steppes, and African savannas were interwoven with megafauna such as mammoths, giant ground sloths, and early bison species. coexisting with endemic plant species that formed resilient, seasonally dynamic communities. Human-driven land conversion, overgrazing, and climate variability gradually reduced these expanses, causing the disappearance of both flora and fauna adapted to their rhythms. The sensory presence of wind sweeping through tall grasses, the scent of earth and sun-warmed vegetation, and the distant calls of now extinct species are experiences reconstructed only through ecological modeling and paleoecological studies. High in mountain ranges and alpine regions, ecosystems clung to fragile microclimates. Glacial retreat, warming temperatures, and geological shifts erased pockets of unique flora and fauna, often restricted to narrow elevational bands. Alpine meadows, once dotted with endemic flowering plants and cold-adapted insects, vanished as temperatures rose and snow cover receded. These ecosystems, finely tuned to cold, oxygen-thin conditions, left only fossil pollen and occasional preserved plant material as evidence of their former existence. The quiet winds, the tactile cold of ice underfoot, and the sparse, fragile vegetation are traces that persist only in scientific reconstructions. Freshwater ecosystems, rivers, lakes, and streams have similarly suffered the loss of unique assemblages of species. River channels once meandered freely, creating oxbow lakes and floodplains that supported diverse fish, amphibians, and invertebrates. Damming, water diversion, and pollution have erased many of these habitats entirely. Certain freshwater species recorded in historical accounts or preserved in specimens are now extinct. Their absence reshaped not only the aquatic food webs, but also the surrounding terrestrial habitats that depended on periodic flooding and nutrient deposition. Islands, small and remote, often hosted ecosystems of extreme endemism. Madagascar, the Caribbean islands, and isolated Pacific atolls held species found nowhere else, including lemurs, giant tortoises, and flightless birds. The introduction of invasive species by humans, habitat clearing, and climate events drove many of these communities to extinction. The isolation that once allowed evolution to explore unusual forms and behaviors became a vulnerability when environmental pressures changed rapidly. Fossils, subfossil remains, and written records provide the only windows into these vanished island worlds. Even polar and subpolar regions contain specialized ecosystems now altered beyond recognition. Tundra pockets and ice-dependent communities in the Arctic supported plants and animals adapted to extreme cold and seasonal light cycles. As ice sheets melted and ocean currents shifted, some of these ecosystems disappeared entirely, leaving genetic traces and fossilized remnants as evidence. Ice core studies revealed the plant and microbial life that once thrived beneath ice margins, recording climate shifts that shaped what could exist in these frozen regions. Finally, in the more recent centuries, human activity has accelerated the disappearance of ecosystems on a scale unprecedented in Earth's history. The Atlantic forest of South America, ancient Yangtze River wetlands, and old-growth forests of Europe and North America have been reduced to fractions of their original extent. Species once common within these environments vanished as their habitats were fragmented, drained, or cleared. Scientific reconstructions, satellite imagery, and paleoecological studies document the rhythm and loss of these systems, providing both knowledge and a quiet melancholy for what can no longer be experienced directly. Through the lens of science, we glimpse the textures, sounds, and interactions that defined ecosystems now gone. Fossilized pollen, sediment cores, and preserved specimens offer clues to the intricate balances of water, light, nutrients, and life forms. Each extinct ecosystem teaches lessons about climate, adaptation, resilience, and vulnerability. They remind us that the present is built atop layers of vanished worlds, that the complexity and beauty we see today are the survivors of past extinctions, and that understanding what has been lost is crucial to appreciating and conserving what remains. As we reflect, we recognize that while we may never walk through these lost ecosystems, we can sense their presence in the quiet details recorded by Earth's enduring archives. The whisper of a prehistoric fern, the shimmer of a coral no longer living, or the brush of wind through a vanished prairie can still be felt in our understanding and careful observation. By studying them, we honor both the fragility and resilience of life, and in that knowledge, find a calm, contemplative connection to the vast and intricate story of our planet. In the Carboniferous forests, the density of plant life was unlike anything we witness today. Towering lycophytes, some exceeding 30 meters in height, dominated the canopy, their needle-like leaves forming intricate patterns against the filtered sunlight. Beneath them, a dense undergrowth of ferns, club mosses, and horsetails created a spongy carpet that trapped moisture and nourished countless invertebrates. The air was thick and humid, rich with the earthy scent of decaying plant matter, a fragrance now confined to the pages of paleoecology. Early amphibians, such as temnospondyls, moved cautiously through the shallow pools, their skin glistening under dim light that penetrated the forest canopy. Fossilized trackways reveal how these creatures navigated the waterlogged terrain, providing a silent record of daily activity in ecosystems that no longer exist. Moving to ancient wetlands, peatlands formed slow, layered accumulations of partially decayed organic matter. European and North American wetlands were centers of biodiversity, hosting a myriad of plant species adapted to saturated soils. Sediment cores extracted from former fen sites show pollen from sedges and reeds, reconstructing the vegetation that once swayed in gentle currents of water. Invertebrate populations, including now extinct species of snails and insects, thrived in these habitats, while birds and amphibians relied on seasonal flooding to reproduce. The disappearance of many of these wetlands was gradual but profound, as human drainage projects in the past millennium transformed landscapes into fields and pastures, permanently altering hydrology and erasing the intricate web of life that had persisted for millennia. Beneath the ocean, coral reef ecosystems of the Paleozoic and Mesozoic eras displayed forms that no longer exist. Fossil evidence reveals colonies of tabulate and rugose corals that built complex, three-dimensional structures in shallow tropical seas. These reefs were hubs of biodiversity, sheltering mollusks, brachiopods, trilobites, and early fish. In some regions, Permian reef systems were abruptly decimated by mass extinction events, leaving behind limestone formations as the only record of once vibrant underwater cities. The textures of coral surfaces, now mineralized, can be observed in thin sections, revealing growth patterns and symbiotic relationships with algae that allowed these ecosystems to flourish under sunlight filtered through warm waters. Modern coral declines echo these ancient losses, though the scale of anthropogenic change today far surpasses natural historical shifts. Grasslands, too, hold a record of life long vanished. North American prairies once hosted mammoths, giant ground sloths, and horses with no modern descendants. Paleoecological evidence from pollen and coprolites shows a rich diversity of grasses, flowering plants, and seasonal blooms that structured animal migration and feeding patterns. The Eurasian steppes supported similar megafauna, with grasses adapted to cold, dry winters and hot summers, forming a rhythmic pulse of growth, decay, and renewal. The expansion of agriculture and grazing disrupted these cycles, leading to local extinctions of both plant and animal species. Even the tactile sensation of wind moving through high grass, or the distant sound of a now extinct bison herd, can only be reconstructed from fossils, sediment layers, and ecological modeling. High-altitude ecosystems provide another window into vanished worlds. Alpine meadows and glaciers, where specialized flora and fauna adapted to thin air and short growing seasons, were lost as climates warmed and glaciers retreated. Fossil pollen studies in glacial moraines reveal plants uniquely suited to cold, nutrient-poor soils, while preserved insect remains indicate finely balanced food webs. Even slight shifts in temperature could trigger cascading changes, erasing microhabitats that had persisted for millennia. The loss of these alpine communities illustrates the vulnerability of ecosystems confined to narrow climatic ranges and emphasizes how changes in temperature, snow cover, and precipitation patterns can permanently alter life in extreme environments. Freshwater ecosystems provide a further account of extinction and transformation. Rivers once flowed freely, creating floodplains and oxbow lakes, where fish species and amphibians thrived in complex networks of water and sediment. Fossilized fish bones, mollusk shells, and plant impressions in river sediments reveal species that have no modern analogues. Many of these rivers were later dammed or diverted, altering hydrology, temperature, and sediment load, and erasing habitats that had existed for thousands of years. Certain freshwater mussels and amphibians, dependent on specific water chemistry and flow regimes, disappeared entirely. The loss of these ecosystems demonstrates how human alteration of water systems reshapes not only aquatic life, but also the surrounding terrestrial vegetation dependent on seasonal flooding. Islands provide an intimate perspective on lost ecosystems. Madagascar, for instance, held diverse communities of lemurs, giant tortoises, and endemic plants. Subfossil evidence reveals the presence of now extinct giant lemurs and flightless birds, species that were finely adapted to island microhabitats. Introduced species, habitat clearing, and hunting by humans led to rapid declines and eventual extinction. Similarly, Pacific atolls supported insect communities, small reptiles, and endemic plants that vanished following sea level changes or human settlement. The study of these islands highlights the fragility of ecosystems constrained by limited space and resources, and the speed at which unique biological assemblages can be lost when environmental balance is disrupted. Even polar regions, which seem inhospitable, once harbored specialized ecosystems. Arctic tundra pockets supported mosses, lichens, and cold-adapted mammals, while subpolar marine regions were home to plankton blooms, benthic invertebrates, and fish that no longer exist. Ice core analyses reveal ancient microbial life and pollen deposits, showing that even regions covered in snow and ice for most of the year experience cycles of growth and adaptation. As ice sheets retreated during natural warming periods, these ecosystems were reshaped, and some species were lost entirely. The record preserved in frozen sediments provides a subtle yet vivid map of these vanished polar communities. Finally, in the Anthropocene, ecosystems have disappeared at unprecedented rates. Forests, wetlands, rivers, and coral reefs all bear evidence of human-driven alteration. The Atlantic forest of South America, for instance, lost more than 85% of its original extent, erasing countless species and ecological interactions. In the Yangtze River Basin, wetlands and floodplains were drained. An endemic fish species vanished, highlighting the sensitivity of freshwater systems to human engineering. Old-growth forests in Europe and North America were cleared for timber, changing microclimates and eradicating understory plants and dependent fauna. These losses are documented through satellite imagery, historical records, and paleoecological studies, allowing scientists to reconstruct the complexity of systems now largely gone from the planet. Through scientific reconstruction, we sense the textures, smells, and interactions that define these ecosystems. Fossil pollen, sediment cores, preserved plant fragments, and subfossil remains serve as archives of life that once thrived in particular conditions. They reveal the interplay of climate, soil, water, and species interactions that sustained ecological balance. Understanding these lost ecosystems reminds us of both the fragility and resilience of life and the responsibility inherent in conserving those systems still surviving. Each record is a whisper from the past, a gentle reminder of worlds that existed and shaped the earth we inhabit today. In the temperate forests of North America, vast tracts of land once supported ecosystems now entirely altered or gone. Ancient oak-hickory forests stretched across the eastern United States, with understories of shade-tolerant shrubs, mosses, and ferns forming layered habitats for invertebrates, birds, and mammals. Fossilized pollen and charcoal layers indicate that these forests experienced natural fire cycles, which maintained diversity and cleared space for new growth. The arrival of humans, however, introduced large-scale deforestation and land conversion, fragmenting habitats and causing the local extinction of species such as the passenger pigeon, once numbering in the billions, and the Carolina parakeet, whose bright plumage is now seen only in museum collections. The quiet rustle of leaves, the hum of insect life, and the filtered sunlight through a high canopy are sensations that we can only reconstruct in imagination, guided by the evidence preserved in the soil and preserved specimens. Across South America, the Atlantic forest once formed an immense corridor of biodiversity, with towering trees, dense vines, and ephemeral streams, creating microhabitats for amphibians, mammals, and birds. Subfossil records reveal species such as the golden lion tamarin, which survived in fragments, and a host of now extinct invertebrates. The forest's rich soils and warm, humid climate fostered nutrient cycles that supported these communities for millennia. Today, only remnants remain, and much of what was lost is reconstructed from seed banks, pollen cores, and historical accounts, painting a picture of an ecosystem that teemed with life and complex ecological relationships. In Southeast Asia, lowland peat swamp forests, once widespread, were unique repositories of biodiversity. Trees adapted to waterlogged, acidic soils dominated, while aquatic plants thrived in channels and pools. Fossilized seeds and pollen indicate a diverse assemblage of flora, while subfossil remains point to mammals like the now extinct Sumatran tiger subspecies that relied on dense, watery forests for hunting and shelter. As humans drained these swamps for agriculture, logged timber, and converted land to oil palm plantations, these ecosystems disappeared rapidly, and the specialized species that depended on them declined or vanished entirely. The atmosphere of these swamps, thick, humid air, rich with the scent of decaying vegetation, and punctuated by bird calls and insect hums, is preserved only in ecological reconstruction. Marine ecosystems, too, bear witness to profound loss. The ancient reefs of the Triassic and Jurassic periods supported corals, sponges, and early fish in shallow seas, forming complex structures now visible only as fossilized limestone. The extinction events at the end of these periods wiped out entire reef systems and their associated fauna. Later, in the Cretaceous, reef ecosystems flourished again, with rudest bivalves forming reef frameworks and providing habitats for mollusks, echinoids, and fish. These structures, fossilized and buried under sediment, reveal patterns of growth, environmental stress, and recovery. Modern reef loss, due to warming, pollution, and acidification, mirrors these ancient disruptions, though at an accelerated pace, emphasizing the vulnerability of complex marine systems to environmental change. Grasslands and savannas provide additional examples of lost biodiversity. In the North American Great Plains, Pleistocene megafauna like mammoths, mastodons, and giant ground sloths shaped vegetation through grazing and browsing. Paleoecological studies, including fossilized dung, trackways, and pollen analysis, show a dynamic interaction between plants and herbivores. The extinction of these large mammals, combined with human land use changes, transformed the grasslands into ecosystems dominated by smaller herbivores and introduced species, altering fire regimes, soil composition, and plant diversity. The gentle sway of tall grasses in wind, punctuated by distant animal calls, is now a memory encoded in sediments and the bones of vanished creatures. Alpine and montane ecosystems illustrate the fragility of life in extreme environments. Fossilized pollen from mountain meadows and moraines reveals plant species adapted to short growing seasons, cold temperatures, and high UV exposure. Insects and small mammals specialized to these microhabitats faced extinction when glaciers melted and temperatures rose, altering moisture availability and seasonal patterns. These communities, though small in area, played a critical role in ecological networks, linking highland and lowland species through seasonal migration and nutrient cycling. The sensation of crisp air, rocky terrain underfoot, and the sparse but vibrant floral displays is preserved only in paleobotanical records and careful field reconstructions. Freshwater ecosystems offer yet another lens into loss. Ancient river systems in Africa, Asia, and South America hosted diverse fish and amphibian populations adapted to seasonal flooding and stable hydrological cycles. Fossilized fish teeth, shells, and plant impressions provide evidence of species that no longer exist, while sediment cores reveal historical water chemistry and nutrient cycles. Human activities, including damming, irrigation, and pollution, have altered river flows and water quality, eliminating habitats and driving extinctions. The sound of flowing water, the tactile coolness of a riverbed, and the delicate structures of aquatic plants are sensations we reconstruct scientifically, connecting with ecosystems that vanished within living memory. Islands, too, are laboratories of both evolution and loss. In Madagascar, subfossil remains reveal a rich diversity of now extinct lemurs, giant tortoises, and flightless birds. Human arrival and habitat conversion led to rapid extinctions, eliminating unique evolutionary lineages. The Galapagos Islands, while partially preserved, lost species like the Floriana tortoise and several finch populations to introduced predators and environmental change. Fossil evidence, skeletal remains, and detailed ecological records allow reconstruction of these lost island ecosystems, offering insights into how isolation shapes biodiversity and how fragile such systems are when disrupted. Even in polar ecosystems, the historical record reveals intricate ecological webs. Ice core analyses in Greenland and Antarctica uncover pollen, microbial life, and dust layers, indicating the presence of tundra plants and cold-adapted animals in regions now dominated by ice. Seasonal blooms of plankton in polar oceans supported rich food webs, including invertebrates, fish, and marine mammals, some of which are now extinct or severely diminished. As ice sheets advanced and retreated over millennia, these ecosystems appeared and disappeared, a natural rhythm recorded in frozen archives, highlighting the resilience and fragility of life in extreme environments. In the rainforests of the Paleogene period, roughly 66 to 23 million years ago, tropical canopies stretched unbroken across large portions of South America, Africa, and Asia. Fossilized leaves, pollen grains, and amber-encased insects reveal an intricate network of life where towering trees such as early palms, figs, and leguminous species provided vertical complexity that supported arboreal mammals, reptiles, and birds. These forests were moist and dense, their air rich with the smell of decomposing leaves and resin, the hum of insect activity, and the calls of early primates navigating the upper branches. Many of these ecosystems vanished as global temperatures shifted, continents drifted, and volcanic activity reshaped landscapes, leaving behind fossil records that reconstruct their former abundance. Mangrove forests, now restricted to tropical coastlines, once formed extensive networks along ancient shorelines. These ecosystems stabilized sediments, filtered nutrients, and provided nurseries for fish and crustaceans. Fossilized root structures and pollen grains indicate that mangroves in regions such as the Tethys Sea covered far larger areas than today, supporting species that no longer exist. Changes in sea level, sedimentation, and human exploitation have dramatically reduced these ecosystems, making their past expanses visible only in sedimentary deposits. The tactile structure of pneumatophores, the salty tang of brackish waters, and the quiet movement of juvenile fish through shallow roots are sensations preserved in geological and paleobiological evidence. In the freshwater floodplains of South America, the Miocene epoch revealed a richness of life that no longer exists. Fossilized fish, amphibians, and aquatic plants indicate dynamic networks of rivers, lakes, and wetlands. The ecosystems supported herbivorous mammals, crocodilians, and birds dependent on the intricate hydrological patterns of seasonal flooding. Sediment layers show cycles of drought and inundation, which shaped species adaptation and community composition. Human-driven transformation of rivers, deforestation, and wetland drainage in more recent centuries have eliminated many of these habitats, erasing unique ecological interactions. Reconstruction from cores, fossils, and ecological modeling provides insight into species behaviors, plant growth patterns, and water dynamics that have been lost from the living world. The deserts of the past, too, held ecosystems now vanished. North African and Middle Eastern deserts in the Miocene and Pliocene hosted savanna-like oases, with grasses, shrubs, and ephemeral pools supporting herbivorous mammals and predators adapted to sparse but seasonally productive conditions. Fossilized dung, teeth, and plant remains reveal the interplay between flora and fauna, as species tracked water availability and resource distribution across the arid landscape. Over geological time, increased aridity and climatic shifts transform these regions into hyper-arid deserts, eliminating species and habitats once abundant. The whisper of dry wind over sand, the shimmer of heat mirages, and the sparse vegetation are now accessible only through scientific reconstruction. Coastal ecosystems provide additional examples of disappearance. Barrier islands, estuaries, and tidal marshes that once buffered shorelines and supported migratory birds have been extensively modified by sediment shifts, sea level rise, and human development. Fossil shells, mangrove pollen, and sedimentary structures indicate the past complexity of these habitats, where crabs, mollusks, and wading birds thrived. Urban expansion and shoreline modification have reduced these systems, leaving only fragments of their former ecological intricacy. The sensory experience of mud between toes, salt in the air, and the rhythmic sounds of tidal movement are reconstructed through paleoecology and careful observation of remaining habitats. Mountain ranges across the globe, from the Andes to the Himalayas, reveal ecosystems that existed during past glacial and interglacial periods, but are no longer present. Fossilized plants from moraines and glacial valleys show assemblages adapted to cold, oxygen-poor environments, while preserved insect remains indicate tightly balanced food webs. Glacial retreat and warming climates transformed alpine habitats, leading to the disappearance of species specialized to high-altitude niches. Sediment cores, pollen analysis, and preserved fossils allow scientists to reconstruct these environments, revealing both their beauty and vulnerability. Isolated lakes, such as those that once dotted the African Rift Valley, contained unique fish species and aquatic invertebrates, many of which have disappeared. Fossilized fish, skeletons, and sediment records indicate complex ecological relationships, including predator-prey dynamics and nutrient cycling, now disrupted by droughts, sedimentation, and human diversion of water. Lakes that dried completely over centuries left behind only mineral deposits, fossils, and cores to reconstruct their lost ecosystems. The gentle lapping of water, the reflective surface under sunlight, and the rich, layered aquatic vegetation are now memories preserved in scientific records. In polar oceans, the loss of sea ice has erased habitats that supported cold-adapted plankton, fish, and invertebrates for millions of years. Fossil evidence shows cyclical expansions and contractions of ice, each reshaping marine communities and influencing global nutrient cycles. Ice cores reveal trapped microorganisms, algal blooms, and sediment particles that document the historical presence of species now extinct or diminished. These ecosystems demonstrate the delicate balance of temperature, salinity, and seasonal ice coverage in maintaining biodiversity, and how shifts in these parameters lead to permanent ecological change. Throughout human history, the loss of ecosystems has accelerated. Ancient forests in Europe were cleared for agriculture, river systems were redirected, wetlands drained, and coastal marshes converted. Fossil records and historical documentation reveals species that once existed alongside human civilizations, now entirely absent. Extinct birds, fish, mammals, and plants are preserved in museum collections, sediment cores, and written accounts. By studying these records, scientists can reconstruct food webs, seasonal cycles, and species interactions, offering insights into ecosystems that have disappeared within living memory. Across continents, the interplay of climate change, geological shifts, and human activity illustrates the transience of habitats. Fossilized flora and fauna, sedimentary structures, and preserved microbial life provide glimpses into the texture and rhythm of vanished ecosystems. The hum of insects, the rustle of leaves, the splash of fish, and the whisper of wind across grasses are preserved not in the living world, but in meticulous scientific reconstruction. Through these records, we maintain a connection to ecosystems that shape the planet and its biodiversity, a quiet testimony to life that once thrived and can never be directly experienced again. During the Eocene epoch, approximately 56 to 34 million years ago, Earth experienced a period of remarkable warmth, allowing tropical and subtropical ecosystems to extend far beyond their modern ranges. In regions that are now temperate or even boreal, lush forests thrived with broad-leaved evergreen trees, palms, and early magnolias. Fossilized leaves, fruits, and pollen indicate a diversity of understory plants that provided food and shelter for small mammals, birds, and reptiles, many now extinct. Insects preserved in amber reveal intricate ecological relationships such as pollination, herbivory, and predation, offering an unparalleled glimpse into the complexity of these lost systems. The disappearance of these ecosystems came gradually with global cooling, continental drift, and the evolution of more temperate climates, leaving only fossil evidence and sedimentary deposits as testimony to these vanished forests. Mangrove ecosystems, which extend into estuaries and shallow coastal waters, also existed far more widely in the past. Fossilized roots and pollen grains demonstrate that these habitats once stabilized coastlines, provided nurseries for juvenile fish, and supported crustaceans and mollusks in abundance. The loss of ancient mangroves due to natural shoreline changes and human exploitation resulted in the disappearance of numerous species adapted exclusively to brackish waters. The sensory experience of water flowing gently around intricate root networks, the subtle shifts of mud underfoot, and the cry of wading birds is now reconstructed only through sedimentary records and ecological studies of surviving remnants. In prehistoric river floodplains, such as those in the Miocene African Rift Valley, freshwater fish, amphibians, and aquatic plants formed complex communities. Fossilized fish scales, teeth, and plant impressions provide a record of species that no longer exist. These floodplains were subject to seasonal inundation and drought, cycles which shaped the life strategies of both flora and fauna. Over time, climatic shifts and human activities disrupted these hydrological patterns, leading to the loss of species and habitats. The gentle lap of water, the murmur of reeds swaying in current, and the interplay of predator and prey in these wetlands can only be traced through paleoecological reconstruction and modeling. Grasslands, steppes, and savannas across the world tell stories of co-evolved interactions between plants and herbivores. In North America, the Pleistocene prairie hosted mammoths, giant ground sloths, and horses that grazed and browsed across a mosaic of grasses, forbs, and shrubs. fossilized dung and skeletal remains indicate migratory patterns, feeding strategies, and the ecological impact of these large herbivores on vegetation structure. Similar dynamics existed in the Eurasian steppes, where now extinct megafauna-shaped plant communities influenced fire regimes and maintained soil fertility. The loss of these species, combined with human-driven habitat changes, altered the ecological balance, leaving modern grasslands simplified and missing key interactions that once maintained biodiversity and ecosystem function. Alpine and montane ecosystems, once more widespread in cooler glacial periods, were home to specialized plant and animal species. Fossil pollen from high-altitude meadows reveals flowering plants adapted to extreme conditions, while preserved insect remains suggest finely tuned food webs. As glaciers melted and temperatures rose during interglacial periods, these species were forced into shrinking refuges or disappeared entirely. The tactile experience of rugged terrain, cold winds, and short, vivid floral seasons is preserved in the scientific record, giving insight into the fragility of life at the edges of habitable climates. Island ecosystems offer remarkable examples of lost biodiversity. Madagascar, the Caribbean, and Pacific micro-islands hosted species found nowhere else, with evolutionary paths shaped by isolation. Subfossil lemurs, giant tortoises, and flightless birds reveal highly specialized adaptations to their environments. Human colonization, introduction of invasive species, and habitat clearance cause rapid extinctions, erasing entire evolutionary lineages. Fossilized bones, teeth, and plant remains allow scientists to reconstruct these lost communities, revealing not only the species themselves, but also their ecological roles and interactions. Polar and subpolar ecosystems provide evidence of both resilience and vulnerability. Ice cores and sediment records from Greenland, Antarctica, and the Arctic Ocean reveal microfossils, pollen, and ancient microbial life, indicating the presence of tundra and cold-adapted marine ecosystems during warmer intervals. Plankton blooms supported fish and marine mammals, while tundra plants supported herbivores and insects. As ice sheets advanced or retreated, ecosystems were forced to shift or disappear, leaving behind records that document cycles of adaptation and extinction. These lost ecosystems illustrate how life responds to extreme environmental change and how delicate the balance can be in regions of low biodiversity redundancy. In the Anthropocene, human influence has accelerated the disappearance of ecosystems at unprecedented rates. Coastal marshes, wetlands, old-growth forests, rivers, and coral reefs have been altered or destroyed, resulting in the extinction of species documented in museum collections or historical records. The Atlantic forest, once covering large portions of South America, is now fragmented into small patches, while European old-growth forests have been cleared for centuries, eliminating native fauna such as large predators and understory specialists. Coral reefs worldwide face bleaching and acidification, parallel to ancient extinction events, but accelerated by industrial-era climate change. Fossil evidence, paleoecological data, and historical accounts allow reconstruction of these ecosystems, showing a level of complexity, interdependence, and richness now largely lost. Through careful study of fossils, sediment cores, pollen records, and subfossil remains, scientists reconstruct the rhythms of these vanished ecosystems. We can sense the flow of water through ancient streams, the hum of insects across wetlands, the brush of wind through prehistoric grasslands, and the filtered sunlight of lost forests. Each reconstruction reveals how species interacted with each other and with their environment, forming networks that maintain balance, resilience, and diversity. These ecosystems, once vibrant and self-sustaining, now exist only in records preserved beneath layers of earth and in the meticulous observations of researchers dedicated to understanding the past. By reflecting on these lost ecosystems, we understand the impermanence of habitats and the intricate connections that sustain life. Fossilized pollen, preserved bones, sedimentary layers, and subfossil remains offer clues about climate patterns, species interactions, and ecosystem resilience. Each vanished forest, reef, wetland, grassland, and alpine meadow is a testament to the dynamism of Earth's biosphere and a reminder that what exists today is both precious and fragile. Through knowledge, observation, and careful study, we maintain a quiet connection to these worlds, honoring life that thrived long before human observation, and that may never be experienced again in the living world. In the Miocene rainforests of South America, extensive canopies stretched uninterrupted across vast lowlands, fostering a remarkable diversity of life. Fossilized leaves, seeds, and pollen reveal a complex mosaic of palms, leguminous trees, and early figs. Small mammals, reptiles, and birds navigated the vertical structure of these forests, while insects, many preserved in amber, engaged in pollination, herbivory, and predation. These ecosystems were humid, warm, and alive with constant movement. Streams meandered through the undergrowth, their banks lined with mosses and ferns, creating microhabitats for amphibians. Over time, tectonic shifts and climatic cooling fragmented these forests, and today only remnants remain, with subfossil evidence hinting at the richness that once existed. Mangrove ecosystems of the Paleogene extended far beyond modern tropical coastlines. Fossilized pneumatophores and pollen grains indicate that these habitats once provided nursery grounds for juvenile fish, shelter for crustaceans, and stabilization for shifting sediments. The loss of ancient mangroves, through both natural shoreline changes and human exploitation, led to the disappearance of many species adapted exclusively to brackish waters. Sediment studies reveal complex layering that captured seasonal growth patterns, water levels, and interactions with surrounding marine and terrestrial ecosystems, preserving a record of ecological intricacy now mostly gone. Freshwater floodplains, such as those found in the African Rift Valley, held diverse and now lost communities. Fossilized fish bones, mollusk shells, and plant impressions document species uniquely adapted to seasonal inundation and drought cycles. These floodplains were once dynamic, supporting herbivorous mammals, amphibians, and reptiles that relied on periodic flooding for food and breeding. Changes in climate, sedimentation, and human water management have erased many of these habitats, leaving only fossils and sediment layers to reconstruct ancient hydrological regimes and ecological networks. Grasslands and savannas across North America and Eurasia were once dominated by megafauna, such as mammoths, mastodons, and giant ground sloths. Fossilized dung and skeletal remains reveal patterns of migration, feeding, and ecosystem engineering that maintained plant diversity and soil fertility. These extinct herbivores influenced fire regimes, nutrient cycling, and seed dispersal. Human hunting and climate change during the late Pleistocene accelerated the loss of these large mammals, transforming grasslands into simpler systems dominated by smaller herbivores and introduced species, leaving a legacy of diminished ecological complexity. Alpine and montane ecosystems found on mountain ranges worldwide provide evidence of vanished plant and insect communities adapted to extreme cold, thin air, and short growing seasons. Fossilized pollen, plant macrofossils, and insect remains indicate highly specialized interactions within these microhabitats. Glacial retreat and rising temperatures forced species into shrinking refuges or led to extinction, reducing biodiversity and erasing ecological interactions that had persisted for millennia. Sediment cores and pollen analyses reveal how vegetation and insect populations shifted with climate changes, preserving a record of delicate ecological balance that no longer exists. Island ecosystems demonstrate extreme vulnerability to environmental change and human impact. Madagascar, the Caribbean, and remote Pacific atolls hosted species found nowhere else. Subfossil lemurs, flightless birds, and giant tortoises illustrate evolutionary specialization. Habitat clearance introduced predators, and hunting caused rapid extinctions. Fossilized bones, teeth, and plant remains allow scientists to reconstruct these communities and their ecological roles, revealing networks of species interactions that cannot be directly experienced today. Polar regions held ecosystems finely tuned to cold and seasonal light cycles. Ice cores and sediment deposits in Greenland, Antarctica, and the Arctic show ancient microbial life, pollen, and plankton assemblages that supported fish and marine mammals. Seasonal ice melt created temporary habitats for a diversity of organisms, now largely extinct or diminished. These ecosystems demonstrate the fragility of life in extreme environments and the sensitivity of biological communities to even minor shifts in climate or ice coverage. Human activity in recent centuries has dramatically accelerated the disappearance of ecosystems. Coastal marshes, wetlands, old-growth forests, and river systems have been transformed or destroyed, causing extinctions documented in museum collections, historical accounts, and sediment records. The Atlantic forest in South America, once covering vast areas, now exists only in fragments, while European old-growth forests were cleared over centuries, eliminating native fauna and understory plants. Coral reefs around the world face bleaching and acidification, mirroring ancient extinction events, but at unprecedented speed. Paleoecological reconstruction, satellite imagery, and historical data provide glimpses of the complexity that has been lost. Through careful study of fossils, sediment cores, pollen records, and subfossil remains, scientists can reconstruct the texture and rhythm of vanished ecosystems. We can imagine the flow of streams, the rustle of leaves, the hum of insects, and the gentle movement of grasses and flowers. Each fossil, pollen grain, and preserved bone provides evidence of species interactions, seasonal cycles, and ecosystem dynamics. These ecosystems, once vibrant and self-sustaining, now exist only in scientific records and reconstructions, reminding us of the impermanence of habitats and the delicate balance that sustains life. Reflecting on these lost worlds, we recognize the fragility of ecosystems and the intricate connections that allow biodiversity to flourish. Fossilized pollen, bones, sediment layers, and preserved plant matter provide windows into past climates, species interactions, and ecological resilience. Each vanished forest, reef, wetland, grassland, and alpine meadow stands as a testament to the dynamism of Earth's biosphere, a reminder that what survives today is only a fraction of what has existed. Through careful study, we maintain a quiet, contemplative connection to these ecosystems, honoring life that once thrived and may never be experienced again. In the Miocene coastal plains of Europe, wetlands teemed with life that no longer exists. Fossilized reeds, sedges, and aquatic plants indicate marshy habitats, rich with nutrients, supporting diverse populations of amphibians, birds, and small mammals. Fish fossils reveal species adapted to shallow, slow-moving waters, while mollusk shells provide evidence of intricate ecological networks. Seasonal fluctuations in water levels created dynamic habitats, promoting diversity and shaping the life strategies of resident species. Over centuries, human drainage projects, agriculture, and urban development transformed these wetlands, erasing the delicate balance that had persisted for millennia. The soft scent of wet soil, the sound of water lapping over vegetation, and the subtle movement of aquatic life can now only be reconstructed through sediment layers, fossil evidence, and careful ecological modeling. In the tropical forests of Africa, the fossil record reveals ecosystems even richer than those currently surviving. Pollen, seeds, and plant macrofossils show a high diversity of tree species, including early forms of figs, palms, and leguminous trees, forming dense canopies with multiple layers. Understory plants included ferns, shrubs, and vines that created microhabitats for insects, amphibians, and small mammals. Subfossil remains of primates and small carnivores demonstrate the complex predator-prey relationships that maintained ecological balance. Climatic shifts, volcanic activity, and later human settlement fragmented these forests, causing local extinctions and the disappearance of ecosystems whose intricate connections had persisted for millions of years. Grasslands of the Eurasian steppes also hold a record of vanished biodiversity. Fossilized dung, teeth, and trackways of Pleistocene megafauna, such as steppe bison, woolly rhinoceroses, and wild horses, illustrate interactions with vegetation that shaped plant communities and soil structure. Fire regimes, grazing pressure, and seasonal migrations maintained a dynamic equilibrium, fostering high productivity and diversity. As humans expanded across these regions and climates warmed, many of these large herbivores disappeared, transforming grasslands into ecosystems dominated by smaller mammals and reducing ecological complexity. Sedimentary evidence and fossil analysis allow scientists to reconstruct the once vibrant pulse of life across these plains. Island ecosystems continue to demonstrate vulnerability and uniqueness. In the Mascarene Islands, now extinct giant tortoises and flightless birds once maintained seed dispersal and vegetation structure. Subfossil remains reveal their role in shaping plant communities and maintaining soil health. Human colonization and introduced predators led to rapid extinctions, eliminating ecological interactions that had persisted for centuries. Similarly, the Hawaiian archipelago hosted a variety of birds, insects, and plants that evolved in isolation. Deforestation, invasive species, and habitat modification caused numerous extinctions, which can only be understood through fossil evidence and historical records. Alpine ecosystems in North and South America offer additional examples of loss. Fossilized pollen from high-altitude meadows shows flowering plants adapted to cold, low-oxygen environments, while insect remains indicate specialized feeding relationships and tight ecological networks. As glacial periods ended, These species were forced into shrinking refuges or vanished entirely. Modern mountaintop ecosystems retain some species, but are a fraction of the biodiversity present during colder intervals. Sediment cores, pollen analysis, and fossil remains allow reconstruction of the delicate balance that maintain these high-altitude habitats. Polar oceans, historically home to ice-adapted marine communities, reveal the sensitivity of life to environmental change. Microfossils from Greenland and Antarctica, combined with sediment analysis, document phytoplankton, zooplankton, and fish communities that thrived during warmer periods. Seasonal ice melt created temporary habitats that supported complex food webs, while advances in ice sheets eliminated or displaced species. These cycles of expansion and contraction illustrate how even small shifts in temperature, salinity, or ice coverage can reshape ecosystems entirely. Fossil records preserve subtle details of species, composition, abundance, and ecological interactions lost to time. In the Anthropocene, the pace of ecosystem loss has accelerated dramatically. Forests, wetlands, rivers, coral reefs, and coastal systems have been degraded or destroyed, resulting in species extinctions and the disappearance of ecological processes. The Amazon and Atlantic forests retain only fragments of their former richness, while coral reefs worldwide experience bleaching and mortality due to warming and acidification. Fossil evidence, satellite imagery, historical records, and paleoecological studies allow scientists to reconstruct lost ecosystems, offering insights into the complexity, resilience, and fragility of life. The sensory richness of these habitats, rustling leaves, flowing water, buzzing insects, and calls of animals, now exists only in scientific reconstruction and human imagination. Through careful examination of sediment cores, pollen records, fossilized bones, and subfossil plant matter, scientists uncover the rhythms and textures of ecosystems that no longer exist. Streams meandered through wetlands, leaves fluttered in gentle forest breezes, grasses swayed across vast plains, and coral structures thrived under filtered sunlight. Each fossil, pollen grain, and preserved specimen reveals ecological interactions, seasonal patterns, and the way species shaped and responded to their environment. These reconstructions provide a window into ecosystems that once flourished, offering a quiet reflection on the fragility and impermanence of life on Earth. By studying these lost ecosystems, we gain an understanding of the processes that sustain biodiversity and the consequences of ecological disruption. Fossilized evidence preserves knowledge of climate shifts, species interactions, and habitat changes over millions of years. Each vanished forest, reef, wetland, grassland, and alpine meadow stands as a testament to the dynamic nature of Earth's biosphere and the delicate balance that maintains life. Through scientific reconstruction, observation, and reflection, we maintain a connection to these worlds, honoring the life that once thrived and may never be experienced again in the living present. In the ancient wetlands of North America, prior to widespread human modification, extensive marshes and slow-moving rivers supported a richness of life now largely vanished. Fossilized remains of freshwater mollusks, fish, amphibians, and aquatic plants indicate highly productive systems. These wetlands provided breeding grounds for birds and shelter for small mammals. Seasonal flooding created complex mosaics of habitats, supporting a diversity of species adapted to both dry and inundated conditions. With European colonization, much of this landscape was drained for agriculture, replaced with monocultures and fragmented by dams, eliminating intricate ecological networks that had persisted for thousands of years. Through sediment analysis, subfossil remains, and pollen cores, scientists reconstruct the once lively pulse of these freshwater ecosystems, understanding their original structure, productivity, and species interactions. The temperate forests of Eurasia, stretching from Western Europe to East Asia, once hosted an assemblage of species that no longer exists. Fossilized seeds, leaves, and charcoal layers reveal forests dominated by oaks, beeches, and maples, with layered understories of shrubs and herbaceous plants. Large mammals, such as aurochs, wild horses, and European bison, played crucial roles in shaping vegetation structure and nutrient cycling. Subfossil bird remains indicate diverse avian communities that depended on dense forest canopies and understory shrubs. Human agriculture, deforestation, and urban expansion fragmented these forests, causing local extinctions and permanently altering ecological dynamics. The interplay of light filtering through leaves, the rustle of small mammals, and the hum of insects is now a memory preserved in the fossil record and in ecological modeling. In South America, riverine floodplains and riparian forests, particularly in the Amazon basin, have lost countless species due to habitat fragmentation. Fossilized seeds and pollen, along with subfossil animal remains, reveal a diversity of mammals, reptiles, amphibians, and birds that interacted closely with plant communities. Seasonal river overflows created nutrient-rich soils, promoting plant growth and shaping animal distributions. Modern deforestation and damming of rivers have erased much of these dynamic interactions, leaving only fragments of the once thriving ecosystem. Through careful study, scientists reconstruct the movement of water, nutrient cycles, and species behaviors, preserving a sense of the lost complexity of these floodplains. The Australian continent demonstrates striking examples of ecosystem loss. Pleistocene grasslands and woodlands, once home to giant marsupials like Diprotodon and large flightless birds, were maintained by complex herbivore-plant interactions. Fossilized bones, trackways, and plant remains illustrate how these species influence fire regimes, vegetation patterns, and nutrient cycling. The arrival of humans led to rapid extinctions, transforming landscapes and simplifying ecosystems. Today, modern Australian grasslands and forests are shadows of their former richness, though sedimentary and fossil evidence allows partial reconstruction of species distributions and ecological relationships. Mangrove ecosystems, though tropical, were also widespread in past geological periods. Fossilized root structures indicate that they provided shelter for juvenile fish, crustaceans, and mollusks, while stabilizing sediments and buffering coastlines from storms. Loss of these mangroves due to rising seas, sedimentation, and human exploitation caused extinctions of species adapted specifically to these habitats. Sediment layers capture growth rings of mangrove trees, shifts in water salinity, and seasonal changes, allowing scientists to reconstruct the ebb and flow of these dynamic coastal ecosystems. Coral reef systems, both ancient and modern, highlight the vulnerability of marine ecosystems. Fossilized coral structures from the Triassic, Jurassic, and Cretaceous periods reveal diverse communities of fish, mollusks, sponges, and echinoderms. Extinction events and sea level fluctuations repeatedly reshape these systems. Modern reefs face bleaching, pollution, and acidification, paralleling ancient disruptions, but on much shorter timescales. Studying fossil reefs allows reconstruction of structural complexity, species composition, and ecological interactions that defined reef ecosystems across geological time. In alpine and montane habitats, fossil pollen and plant macrofossils reveal specialized communities of grasses, flowering plants, and shrubs adapted to high altitudes. Subfossil insect remains suggest intricate food webs, with species finely tuned to cold temperatures, short growing seasons, and seasonal snowmelt. As glaciers retreated during interglacial periods, these species were forced into shrinking habitats or disappeared entirely. Modern mountaintops retain some species, but the biodiversity and ecological complexity of past alpine ecosystems are largely gone, reconstructed only through paleobotanical and entomological studies. Island ecosystems continue to illustrate the consequences of isolation and vulnerability. Subfossil remains from Madagascar, the Caribbean, and the Pacific show highly specialized species whose roles shaped entire habitats. Flightless birds, giant tortoises, and endemic plants maintained vegetation structure, nutrient cycling, and seed dispersal. Human colonization, invasive predators, and habitat destruction caused rapid extinctions, erasing interactions that had evolved over millennia. Through fossil evidence, pollen records, and sediment cores, scientists reconstruct these vanished ecosystems, revealing not only the species themselves, but also the intricate ecological webs they supported. Polar ecosystems, documented through ice cores, sediment layers, and fossilized microorganisms, reveal the cyclical nature of ice coverage and its influence on life. Seasonal ice provided habitats for plankton blooms, which supported fish, seabirds, and marine mammals. Fossil records indicate species that have disappeared or been greatly reduced in population due to changing ice conditions. These ecosystems, now partially lost due to ongoing climate change, demonstrate the sensitivity of life in extreme conditions and the complex interactions that existed between species, ice coverage, and seasonal nutrient availability. By integrating paleoecological data, sediment analysis, fossil evidence, and subfossil remains, scientists reconstruct the texture, rhythm, and diversity of ecosystems that no longer exist. Streams meandered through wetlands, leaves rustled in dense forests, grasses swayed across plains, and coral reefs thrived under filtered sunlight. Every fossil, pollen grain, and preserved specimen offers insight into species interactions, seasonal cycles, and the delicate balance of ecological communities. These reconstructions provide a quiet window into life on Earth before human impact reshaped and eliminated countless habitats. Through reflection on these lost ecosystems, we gain insight into the fragility of habitats and the complex interactions necessary for biodiversity. Fossilized pollen, bones, sedimentary layers, and preserved plant matter preserve evidence of past climates, species interactions, and ecological resilience. Each vanished forest, reef, wetland, grassland, and alpine meadow serves as a testament to Earth's dynamic biosphere, reminding us that what exists today represents only a fraction of what has once flourished. By studying and understanding these ecosystems, we maintain a quiet, contemplative connection to worlds that existed long before human observation and that may never be experienced again. In the deserts of North Africa, before the Sahara reached its current arid state, savanna-like environments supported a diversity of life now vanished. Fossilized plant remains indicate grasses, shrubs, and scattered trees that provided sustenance for herbivorous mammals, reptiles, and birds. Seasonal rainfall created temporary pools, supporting amphibians and invertebrates. Fossilized teeth, bones, and dung reveal predator-prey interactions and the movement patterns of large herbivores. Over millennia, increasing aridity, shifting wind patterns, and climate oscillations transform these once productive savannas into the hyper-arid desert we see today. Sediment cores and pollen analysis allow scientists to reconstruct vegetation patterns, water availability, and species distribution in these long-lost ecosystems. In Southeast Asia, Pleistocene forests extended far wider than today, reaching into regions now dominated by agriculture or urban landscapes. Fossilized leaves, seeds, and pollen indicate dense tropical canopies with multiple layers supporting arboreal mammals, birds, and reptiles. Fossilized primates and small carnivores demonstrate complex interactions such as predation, seed dispersal, and territory maintenance. Rising sea levels during interglacial periods submerged lowland forests, fragmenting habitats and isolating populations. Subsequent human activity accelerated species loss, leaving only subfossil remains and sedimentary records to reveal the richness of these vanished forests. In the ancient wetlands of Australia, vast floodplains supported diverse plant and animal communities that no longer exist. Fossilized freshwater mollusks, fish, and plant matter indicate productive habitats maintained by seasonal inundation. Megafauna, such as Diprotodon and giant kangaroos, influenced vegetation structure, nutrient cycling, and seed dispersal. Human hunting and habitat modification contributed to the extinction of many of these species, fundamentally altering ecosystem dynamics. Sediment cores and fossil evidence allow reconstruction of the rhythms of water, plant growth, and animal activity that characterize these lost wetlands. The Caribbean islands reveal ecosystems once shaped by isolation and endemism. Fossilized remains of flightless birds, giant tortoises, and endemic plants illustrate ecological networks evolved over millennia. These species played key roles in seed dispersal, soil turnover, and vegetation maintenance. Human colonization introduced predators and caused deforestation, rapidly extinguishing these unique communities. Fossil records and pollen studies allow scientists to reconstruct lost habitats and interactions, revealing the intricate balance that existed on these islands before human interference. Coral reefs from the Mesozoic and Cenozoic eras provide evidence of repeated ecological turnover and extinction. Fossilized coral structures reveal complex communities of fish, sponges, mollusks, and echinoderms, with species-specific interactions that shaped reef structure and nutrient cycling. Sea level changes, ocean chemistry shifts, and global climatic events repeatedly reshaped reef ecosystems. Modern reefs face threats from warming, acidification, and overfishing, mirroring the challenges of past reefs, but occurring at an accelerated pace. Paleoecological studies allow reconstruction of species, composition, reef architecture, and ecological interactions, preserving knowledge of ecosystems no longer extant. In North America, Pleistocene glacial landscapes supported ecosystems of tundra and steppe, home to species such as mammoths, saber-toothed cats, and giant beavers. Fossil pollen and plant macrofossils reveal vegetation adapted to cold, open habitats. Seasonal variations in ice coverage influenced water availability, food resources, and species movement. human hunting and climate change contributed to megafaunal extinctions, reshaping plant communities and altering ecosystem processes. Sediment analysis, fossil remains, and paleoecological modeling allow reconstruction of these landscapes, providing insight into interactions and environmental conditions that no longer exist. Island ecosystems in the Pacific, such as those in Polynesia, once supported unique avian and invertebrate species. Fossilized bones, teeth, and plant remains reveal networks of species interactions, including specialized pollination and seed dispersal relationships. Human colonization, introduction of invasive species, and habitat destruction caused rapid extinctions. Through paleoecological reconstruction, scientists can understand these interactions, revealing ecosystems that, although lost, demonstrate the consequences of isolation and vulnerability in shaping biodiversity. Polar tundra ecosystems, preserved in permafrost and sediment cores, show communities of mosses, lichens, and cold-adapted invertebrates that existed during past interglacial periods. Fossilized plant remains and pollen indicate seasonal vegetation cycles, while microbial fossils reveal ecological processes in nutrient cycling and soil formation. As ice sheets expanded and contracted, these communities shifted, were displaced, or became extinct. Modern tundra retains only fragments of past biodiversity, reconstructed through paleoecological and geological studies that document the subtle interactions and life histories of species lost to time. Through all these studies, scientists gain insight into the rhythms, textures, and complexity of ecosystems that have disappeared. Each fossil, sediment layer, pollen grain, and subfossil specimen contributes to a growing understanding of ecological interactions, seasonal cycles, and habitat dynamics. We can imagine the sway of grasses across plains, the murmur of water in wetlands, the hum of insects in forests, and the glimmer of sunlight through coral structures. These reconstructions provide a quiet, immersive window into worlds that once existed, reminding us of the fragility and impermanence of life on Earth. Reflecting on these lost ecosystems, it becomes clear how closely biodiversity is tied to climate, geology, and human activity. Fossilized remains preserve evidence of past climates, species interactions, and ecosystem resilience. Each vanished forest, reef, wetland, grassland, and alpine meadow is a testament to the transience of habitats and the delicate balance that sustains life. Through careful study and observation, we maintain a connection to these worlds, honoring the life that once thrived and may never be directly experienced again in the present. In the wetlands of the Amazon basin, during the late Pleistocene, river channels shifted frequently, creating islands of forest and marsh that supported dense concentrations of wildlife. Fossilized fish remains indicate diverse freshwater communities, while subfossil bones of giant sloths and armadillo relatives show complex interactions with vegetation. Sediment layers reveal periodic flooding that redistributed nutrients and seeds, sustaining a mosaic of plant communities. The disappearance of these dynamic floodplain ecosystems resulted from climatic shifts and later human activity, leaving a fossil record that preserves patterns of species distribution and habitat structure. In the Central African rainforests, paleobotanical studies reveal forests with trees reaching extraordinary heights, forming multiple canopy layers. Fossil pollen and leaf impressions indicate a rich understory of shrubs, ferns, and herbaceous plants. Subfossil remains of primates, small carnivores, and arboreal rodents suggest finely tuned predator-prey relationships and seed dispersal networks. Riverine corridors cut through these forests, providing habitat for fish and amphibians. Rising temperatures, tectonic shifts, and later human encroachment led to fragmentation, with many species disappearing entirely, leaving only subfossil evidence of the original ecological complexity. Mangrove forests along the ancient coasts of Southeast Asia supported interdependent communities of fish, mollusks, crustaceans, and birds. Fossilized pneumatophores and pollen grains demonstrate the stabilizing role of these plants in sediment accumulation, as well as their importance as nurseries for juvenile marine species. Changes in sea level, sedimentation, and human exploitation caused local extinctions of specialized organisms, many of which have no direct modern analogues. Sedimentary cores preserve seasonal growth patterns and evidence of environmental fluctuations that once shaped these productive ecosystems. In the grasslands of North America during the Pleistocene, vast herds of bison, mammoths, and horses shaped the landscape through grazing and trampling. Fossilized dung, bones, and plant remains reveal a network of ecological interactions, including nutrient cycling, fire propagation, and plant succession patterns. Predators, such as saber-toothed cats and dire wolves, played key roles in regulating herbivore populations. These ecosystems disappeared following the combined pressures of climate change and human hunting, leaving fossil evidence that allows reconstruction of seasonal movement, grazing intensity, and predator-prey dynamics. Island forests in Madagascar once contained subfossil lemurs, giant tortoises, and endemic birds whose interactions influence vegetation and soil turnover. Fossil pollen, bones, and seed dispersal evidence demonstrate networks of mutualistic relationships. Human colonization, habitat clearance, and introduced predators resulted in rapid extinctions, permanently altering these ecosystems. Paleoecological studies preserve knowledge of species composition, plant-animal interactions, and habitat structure that no longer exist in living form. Alpine zones in South America, particularly in the Andes, hosted specialized communities of grasses, flowering plants, and shrubs adapted to cold, high-altitude conditions. Subfossil insect remains indicate complex trophic relationships with flowering plants and seasonal pollination cycles. As glacial periods ended and temperatures rose, these habitats contracted, forcing species into refugia or causing extinction. Fossil evidence preserves information about vegetation composition, pollinator communities, and ecological interactions unique to these high-altitude ecosystems. Polar marine ecosystems during interglacial periods were supported by seasonal ice melt and nutrient fluxes. Fossilized microplankton, fish remains, and marine mammal bones indicate a productive food web adapted to extreme seasonal conditions. Changes in ice extent, ocean currents, and temperature periodically disrupted these ecosystems, leading to local extinctions. Sediment cores and fossil assemblages allow reconstruction of ecological dynamics, seasonal cycles, and the interactions between ice, water, and life in polar regions. Ancient coral reef systems in the Indo-Pacific, reconstructed from fossilized reef frameworks, show a diversity of coral morphologies, fish assemblages, mollusks, and sessile invertebrates. Fossil evidence demonstrates interspecific competition, predator-prey interactions, and nutrient cycling processes that shaped reef structure. Sea level fluctuations, ocean acidification events, and climatic changes repeatedly altered these systems, leaving behind a record of ecosystems with richness and complexity unmatched in modern equivalents. Floodplain forests in the Miocene of South America demonstrate dynamic hydrology and species interactions. Fossil leaves, seeds, and aquatic invertebrates reveal periodic inundation, promoting plant dispersal and providing habitat for fish, amphibians, and reptiles. Large herbivores, evidenced through subfossil bones and footprints, influenced vegetation patterns, seed distribution, and nutrient cycling. Climatic shifts and landscape changes eventually fragmented these ecosystems, with fossil evidence providing insight into the original complexity, trophic networks, and seasonal rhythms of life. In the savannas of East Africa during the late Pliocene, fossil evidence indicates a mosaic of grasslands interspersed with patches of woodland. Large herbivores, including early ancestors of elephants, giraffes, and antelopes, shaped vegetation patterns through grazing and browsing. Fossilized dung, teeth, and skeletal remains show seasonal migrations and predator-prey dynamics, including interactions with early large carnivores. Periodic droughts and climatic shifts altered water availability, influencing the distribution and composition of flora and fauna. The fossil record preserves these interactions, allowing scientists to reconstruct the ecological balance and species interdependence that existed before modern human influence. In the forests of Southeast Asia, fossilized leaves and pollen indicate a high diversity of dipterocarps, palms, and understory shrubs. Fossil primates and arboreal mammals demonstrate specialized feeding habits and territorial behaviors. Seasonal monsoons created patterns of wet and dry periods, influencing reproductive cycles and plant growth. Rising sea levels during interglacial periods isolated populations, promoting speciation while causing local extinctions. Human land conversion and deforestation further simplified these ecosystems, but fossil and subfossil remains preserve the structure, species composition, and trophic interactions of these lost forests. Pleistocene floodplains of North America, particularly along the Mississippi and Missouri rivers, supported complex assemblages of freshwater fish, amphibians, and aquatic plants. Fossil mollusk shells, fish bones, and pollen layers reveal seasonal flooding that maintained soil fertility and promoted plant diversity. Megafauna, including mammoths and mastodons, influenced nutrient distribution and plant succession. Human hunting and landscape modification contributed to megafaunal extinctions, transforming the ecological network of floodplain habitats. Sediment cores and fossil analysis allow detailed reconstruction of species interactions, seasonal rhythms, and habitat structure that existed before extensive anthropogenic change. Mangrove systems along the coasts of South America, now heavily reduced, once provided critical nursery grounds for fish and invertebrates. Fossilized pneumatophores, pollen, and subfossil fauna indicate highly productive ecosystems with intricate connections between flora and fauna. Sea level rise, sedimentation, and human exploitation caused local extinctions, and fossil records capture both the structural complexity and the ecological processes that sustain these habitats. In the grasslands of Eurasia during the late Pleistocene, steppe bison, woolly rhinoceroses, and horses dominated expansive plains. Fossilized dung, trackways, and bones reveal interactions with vegetation that shaped plant composition, nutrient cycling, and fire regimes. Predatory species, including wolves and large cats, regulated herbivore populations. Climatic warming and human hunting precipitated megafaunal extinctions, simplifying these grassland ecosystems. Sedimentary records, fossil analysis, and modeling allow reconstruction of grazing patterns, predator-prey relationships, and the movement of nutrients through these lost systems. Island ecosystems of the Caribbean and Pacific illustrate extreme evolutionary specialization. Fossil remains of flightless birds, giant tortoises, and endemic plants indicate networks of seed dispersal, vegetation maintenance, and soil turnover. Human colonization, invasive species, and habitat loss caused rapid extinction of these specialized organisms. Paleoecological reconstruction preserves information about species roles, ecological interactions, and habitat complexity, offering insight into the functional dynamics of these now vanished ecosystems. Alpine ecosystems in the Himalayas and Andes reveal plant communities adapted to cold, high-altitude conditions. Fossil pollen, seeds, and subfossil insects indicate complex trophic interactions, seasonal flowering, and pollination cycles. As glaciers receded and temperatures rose, many species retreated into isolated refugia or became extinct. Sediment cores and fossil remains allow reconstruction of vegetation composition, pollinator networks, and habitat structure unique to these alpine regions. Coral reefs of the Indo-Pacific and Caribbean, reconstructed from fossilized reef frameworks, display intricate ecological relationships among corals, fish, mollusks, and other invertebrates. Fossil evidence reveals competition, predation, and symbiosis that shaped reef architecture and species composition. Sea level changes, ocean chemistry shifts, and global climatic events repeatedly reshape these reefs, leaving behind a record of biodiversity and ecological interactions that cannot be experienced directly today. Polar tundra and marine ecosystems reveal highly specialized life adapted to seasonal extremes. Fossilized microplankton, fish, and plant remains indicate productivity cycles tied to ice melt, nutrient availability, and light cycles. Marine mammals and seabirds relied on seasonal abundance, while tundra plants supported herbivores and invertebrates. Ice expansion and retreat caused periodic ecosystem contraction and local extinctions. Sediment and fossil records preserve the subtle details of ecological interactions, species composition, and habitat structure that existed during past interglacial periods. Miocene and Pliocene floodplain forests in South America and Africa provide evidence of dynamic hydrology and complex trophic networks. Fossilized leaves, seeds, invertebrates, and vertebrate remains reveal seasonal inundation, plant dispersal, and species interactions. Large herbivores and carnivores shaped vegetation patterns, soil fertility, and predator-prey dynamics. Climatic and geological changes fragmented these habitats, leaving fossil evidence as the primary source for reconstructing the original ecological complexity. In the arid regions of Central Asia, fossil records from the Pleistocene reveal steppe desert mosaics that supported species now extinct or greatly reduced. Fossilized plant remains indicate grasses and shrubs adapted to low rainfall, while subfossil bones of herbivores such as wild camels, horses, and antelopes show grazing patterns that influenced vegetation structure. Carnivorous species, including large cats and wolves, regulated herbivore populations. Seasonal water sources, reconstructed from sediment cores, created temporary refuges, allowing species to persist during dry periods. These ecosystems largely vanished, are preserved only through paleobotanical and faunal evidence. In the floodplain forests of Southeast Asia, rivers meandered through dense tropical vegetation. Fossilized seeds, leaves, and invertebrates indicate complex food webs, while subfossil remains of primates, birds, and reptiles demonstrate predator-prey dynamics and seed dispersal networks. Human expansion, deforestation, and agriculture have since fragmented these ecosystems, but fossil and sedimentary evidence allows scientists to reconstruct their structure, biodiversity, and seasonal rhythms. Australia's Pleistocene wetlands and grasslands, once home to giant marsupials and flightless birds, reveal ecological complexity through fossilized dung, bones, and plant matter. Herbivores maintained vegetation structure, influenced fire regimes, and distributed nutrients across the landscape. Fossil evidence allows reconstruction of species interactions, movement patterns, and seasonal dynamics. Human arrival and climatic shifts precipitated extinctions, simplifying the ecosystems and leaving only fragments for study. The Atlantic forests of South America, now reduced to small patches, once stretched continuously along the coast, supporting towering trees, understory shrubs, and a diversity of birds, mammals, and amphibians. Fossilized seeds, pollen, and subfossil remains indicate ecological networks, including seed dispersal, herbivory, and predation. Deforestation, agriculture, and urban development have eliminated much of this diversity. But paleo-ecological studies reconstruct the complexity and interdependence of species that existed within these forests. Pleistocene, tundra steppe ecosystems of Siberia and northern Europe, preserved in permafrost, contained herbivores such as woolly mammoths, reindeer, and horses, along with their predators. Fossil pollen, plant macrofossils, and subfossil bones reveal seasonal vegetation patterns, herbivore foraging behavior, and predator-prey interactions. As ice sheets retreated, climatic warming and human hunting reshaped these ecosystems, leading to extinctions and restructuring of plant communities. Sediment and fossil records provide detailed insight into the composition and dynamics of these lost habitats. Coral reef ecosystems of the Caribbean and Indo-Pacific during the Holocene show. Repeated cycles of growth, bleaching, and recovery documented through fossilized reef structures. Fossil evidence indicates species diversity, predator-prey relationships, and mutualistic interactions among corals, fish, mollusks, and sponges. Human activity, combined with natural sea level changes and oceanic shifts, altered these reefs, causing the disappearance of numerous species and functional relationships. Sediment and fossil records preserve the intricacies of these systems that no longer exist in their original form. Island ecosystems of the Indian Ocean, including Madagascar and the Mascarene Islands, contain species with unique ecological roles. Fossilized bones of giant lemurs, tortoises, and flightless birds show interactions with vegetation, seed dispersal, and soil turnover. Habitat destruction, invasive species, and hunting by humans caused extinctions that disrupted ecological networks. Paleo-ecological reconstruction of these islands provides insight into the structure and functioning of ecosystems that evolved in isolation and no longer exist. Polar marine and tundra ecosystems provide evidence of adaptation to extreme seasonal conditions. Fossilized microplankton, fish, marine mammals, and plant remains indicate productivity tied to ice melt and nutrient availability. Changes in ice coverage and ocean currents periodically reshape these ecosystems. causing local extinctions and alterations in species composition. Sediment cores and fossil assemblages allow reconstruction of seasonal cycles, trophic interactions, and habitat dynamics that existed long before contemporary climate change. In the final examples, Miocene and Pliocene floodplain forests in Africa and South America highlight dynamic hydrology and intricate species networks. Fossilized leaves, seeds, invertebrates, and vertebrate remains indicate seasonal inundation, plant dispersal, herbivore activity, and predator-prey interactions. Geological and climatic changes fragmented these ecosystems, yet sedimentary and fossil evidence preserve patterns of vegetation, species interactions, and ecological processes that cannot be observed in living ecosystems today. The collective study of these vanished ecosystems, from deserts and savannas to wetlands, forests, coral reefs, and alpine zones, allows for a meticulous reconstruction of Earth's ecological history. Fossilized pollen, bones, sediment layers, and subfossil plant matter capture rhythms of life, seasonal cycles, species interactions, and habitat dynamics. Streams once flowed through wetlands, leaves rustled in dense forests, grasses swayed across plains, coral structures supported myriad species, and ice-dependent marine communities thrived. These ecosystems no longer exist, but their complexity and interdependence are preserved in the paleontological record. As we close our exploration of these lost ecosystems, take a deep breath and imagine the quiet patterns of life that once existed, the gentle movement of water, the subtle sway of plants in wind, the intricate interplay of species within their habitats. Fossil evidence, sediment records, and careful scientific study allow us to witness, with the mind's eye, the ecosystems we will never see again.